maybe the last 2 videos that you will ever have to watch ever. So I know that some of you don't like these videos, but you're going to have to suck it up, because I don't care. Nah! Michael loves them. Felicia loves them. Doug and Patrick do not love them, but it's okay, Doug and Patrick. You'll be okay, I promise. It's 11 slides. We can do this. Okay. In this chapter, we're continuing on with like that chapter 27 where we were talking about how scientists, modern physicists, thought that light acted more like particles instead of like waves. So remember that in chapter 24, which is what we've been working on in class, that's where we're thinking that light acts more like waves. But chapter 27 was where light acts more like particles. And in this chapter, chapter 28, they're going to try to show you that there is a combination between the both of them, that we can see both. Okay? So let's start with photons are to be treated with no mass. We've already talked about this before, that photons are massless, and that photons are nothing but a pure pocket of energy. Specifically, I can say that a photon is the same thing as what? Michael, do you remember? Felicia, do you remember?
A quantum.
Very good. A quantum. So photon and quantum of energy are the exact same thing. Okay, so photons, we treat them with no mass, and they're just nothing but pure energy. So only pure energy. If we did treat them with mass, their energy would be infinite. And we know that we have to have some type of energy conservation. So if they just continue to have an infinite amount of energy, then lots of things in our universe couldn't work the way that we think that they do. So, no mass. In 1924, there was a dude named de Broglie. De Broglie suggested that there may be symmetry between waves and particles. So maybe there's a relationship between light acting like waves and then also light acting like particles. He thought that if light behaves like particles, then perhaps material particles like electrons may exhibit some wave-like properties. So what you need to know here, de Broglie thought light, specifically electrons, could exhibit wave properties. So light, specifically electron, de Broglie thinks electrons can exhibit wave properties. Now we know electrons are just these tiny little particles. If we think about photoelectric effect, we know light comes down and hits a surface, and then electrons are ejected then from that surface. So we see them as tiny little particles. But de Broglie thinks that maybe instead of light coming down, hitting a surface, and then the electrons coming off as individual electrons, maybe it looks more like that, where there's a little stream of electrons that flow like in a wave-like pattern. That's what he's saying. Okay? He also says, which this is a really important part for him, a moving particle with momentum has a wave associated with it. So he is trying to say something about momentum. So in this, we've seen some equations. We know a lot of these variables. We know that momentum is with that little funny Greek letter. Do you remember what that Greek letter is called?
Wait, which one?
The funny P.
Do
you remember? Do you remember?
Shoot.
Poop. It's up high.
Is it epsilon? Is it,
Think of the little hamsters that the guy trained in the Geico commercial. They say...
Wheel.
Row. This is Greek letter rho. Okay, so this, though, represents momentum. Oh my goodness. We know that momentum equals something times something. Do we remember this? This was so long ago. What is it, Jonathan?
Mass times velocity.
Mass times velocity. Very good. Momentum equals mass times velocity. Okay? So just remember that in the back of your mind. But I want us to look at this. All of these things equal one another. Momentum is equal to the amount of energy divided by the speed of light. So momentum equals that total amount of energy over c, which we know is just the speed of light. What number is that?
3 times 10 to the 8th.
3 times 10 to the 8th meters per second. I know from the last chapter that Einstein said that energy is equal to what? What did Einstein say? Energy is equal to this times this. H times F. What's H?
A constant.
Who's constant?
That guy.
Starts with a P.
Planck.
Planck. Planck's constant times frequency. I like how you know all of this and you're not even in this class.
That was in our physics class.
Oh,
So
good.
it's on the side.
Okay, so
Don't encourage him.
if E equals H times F, that's why they substituted H times F right here. So instead of saying E over C, I could say HF over C. Okay? So that's where we get here. They then have instead F over C will also give me 1 over wavelength. So that's why they did this. So this can also equal H over lambda, and we know that lambda equals our wavelength. How will you always be able to find H? In the front of your test booklet. How will I always be able to find C? Where? Okay, well you know it too, but also because it will be in the front of your test booklet. Okay, so all of these things, those are all equal to one another. Now, this is just to find the momentum of a photon. So momentum of a photon I can find using E over C. Maybe they didn't give me just the energy, maybe they gave me frequency and speed of light. So then I could use this one. Or maybe they didn't give me the frequency at all, maybe they just gave me wavelength, and I could use momentum equals H over lambda. Okay, so you have 3 different ones here, but they're all derivatives of each other. The de Broglie hypothesis...
Wait, can you rewrite the middle part? Because you can't see it because there's a glare on here.
That one?
Mm-hmm.
Is that the one you wanted? Could you tell, though, that I meant, like, with Einstein, E equals H times F, and so we can just substitute where E is with HF? Does that make sense? Okay. Guys, I really need you to be quiet, because this is really important that they understand this stuff. So you have to be quiet. Okay, so the de Broglie wavelength, or the de Broglie hypothesis, was mostly him focusing, instead of electrons acting like particles, they tried to act more like waves. So he thought that he could calculate... Chris.
I wasn't even talking.
Okay.
Nice toe.
No look Indian.
That was too far. Okay,
Just
back on
far
me, back on me.
enough.
You said it other kid.
The de Broglie hypothesis, de Broglie again, he thought that electrons would act more like waves instead of like particles. So he was trying to find the wavelength that these particles, these electrons, would flow with. So our lambda represents what? What does lambda represent? Wavelength. So wavelength equals, what's H?
Your constant.
Planck's constant. What's this little rho, this little P?
Momentum.
That's my momentum. Momentum is equal to what times what?
Mass times velocity.
Mass times what? Velocity. So H over P is the same thing as H over M times velocity. Okay? So these are our formulas. You will need to know, I think on your formula page, I give you momentum equals H over lambda, and you're also going to need to know that lambda equals... I mean, aren't these two just derivatives of one another? You should be saying yes, because they are.
Oh, that's what derivative.
Well, they say that mathematicians shouldn't drink and derive.
Okay,